My name's Fritz Klassner. I'm the Natural Resource Program Manager with the Office of Maunakea Management. This is the Maunakea Speaker Series. Thank you all for coming. Introduce Dr. Ken Hahn. Ken is an ecology professor here at UH Hilo. Has been with UH Hilo for about 20 years now. Before that was with the Hawaiian Volcano Observatory, the US Geological Survey up the hill south of here in Hawaii Volcanoes National Park.
Tonight I want to talk a little bit about Mauna Kea and the other volcanoes that surround it. And Mauna Kea's got a really interesting story of its own, and it's kind of unraveled over the last 20 years, 30 years, really starting in the mid-80s. The story started on the seafloor, really, of Mauna Kea. So what we know about it today, and there's like lots of little clues, and geology is really detective work. There's an awful lot of detective work in it, where you're looking at little things and going, that's weird. And it's always the weird little thing you don't understand that's really pounding on your head going, look at me, look at me. And you're going, no, I don't want to look at you. No, I don't. And go away. Because it doesn't fit with your idea of what it should be, right? And so we're always like looking for things, and it's the thing that makes your head hurt that always is the thing that is got some big story. And we'll see there's just a little teeny piece of something that gave this story away early. And a guy named Robin Holcomb is the first guy that tipped on the main part of unraveling the story of the relationship of Mauna Kea around the surrounding volcanoes. And so this is a picture of the 1984 eruption of Mauna Loa. So the 1984 flow, this is going down the rift zone of Mauna Loa right in here, headed into the saddle right in here, and Mauna Kea in the background. So I call this a story of sibling rivalry because these Hawaiian volcanoes, Kohala, Mauna Kea, Maunaloa, and not really, Huala is kind of on the periphery of the story. It's still duking it out with Mauna Loa, but it's not really in the main part of this story. So we're going to be looking over, oops, hit the wrong button. So here is Mauna Kea, and over in here is Kohala, and this is a great graphic that was produced by a map maker for the National Park Service. Here's Mauna Loa, here's the saddle area in between. So we're looking at these three volcanoes mainly tonight, Kohala, Mauna Kea, and Mauna Loa volcanoes. And these guys, of course, are two really big volcanoes, Mauna Loa and Mauna Kea. Kohala is a lot smaller, right? It's only about 6,000 feet high. 13,800 feet high, 13,700 feet high. But Mauna Loa is a little bit different. They've measured the height of Mauna Loa, particularly when people first started surveying it in the 1800s. They come along and they'd measure it, and it would be something height. And then the next guy would come along and measure it, and it would be like 10 feet different or 5 feet different. And they'd go, well, that guy didn't know how to survey. And then they would come along and somebody else would measure it. Well, neither of those two guys knew how to survey because here's a different height for it. And it was quite a little while before people figured out that it was actually changing in height, right? As magma comes into it, it goes up, and as magma goes out, it goes down. And it was particularly active in the 1800s and early 1900s. So it was kind of like, what is high is kind of an interesting problem on these things. But so I call this sibling rivalry, right? Because there's a lot of this going on, and geologists had this big thing. Mauna Kea is bigger than Mauna Loa. No, Mauna Loa is, or Mauna Kea is taller than Mauna Loa. Mauna Loa is bigger than Mauna Kea. Which one is the biggest one? And inside of that rivalry really is a lot of stuff about how the volcanoes form, what their actual real shape is, right? These volcanoes are sitting against each other, so they grow together in strange patterns, and they're actually interlocked in a lot of really complicated ways. We don't understand the finer points of how they're actually built because most of it is underneath the surface. But we do know that they sit on top of each other, and they're also intertongued with each other in a complicated way. And so I don't know if you guys have ever done that or not, but this is the taller, smarter, bigger. And tonight we're talking about taller, higher, bigger, kind of, for these things. So this whole talk is based on a phone call I got about 10 years ago from somebody who'd been on Jeopardy and missed this question and wanted to know the truth of it, right? So they said, I was on Jeopardy and they asked me, what's the tallest mountain? And I said, Mount Everest. And they said, no, Mauna Kea. So what does that mean? What is taller? What is higher? What are all those things? So that's what we're going to talk about tonight a little bit, is the world's tallest mountain, and what does that actually mean to be the world's tallest mountain. So to get a little background on this, we have to understand how the volcanoes are created. So here's the big island right here, and we're sitting over something that's been named the Hawaiian hotspot. And as I tell my kids in class, it's named that because we're geologists. And so if we can't turn it into Greek or a Latin word, then we just have to use the obvious. So hotspot means it's a spot and it's hot. Yep. And how do we know it's hot? Well, molten rock's coming out of the ground over there on the south end of the island, right? So we're pretty sure that's warmer than the average piece of Ohio. So we know there's a hot place under here someplace, and rock is melting because, duh, we can see the rock come to the surface. Geologists, if we were smarter, we'd be physicists, right? But we're not, we're geologists. So we have to take what we can and work with it. But we look at this kind of thing, and one of the things that's interesting is if you look along the Hawaiian Island chain, a lot of people noticed, Hawaiians noticed, all sorts of people that first came here, is if you look on here, this end of the island chain that we're on the big island is a lot bigger. Why it's called the big island, right? So, and then we look and islands get more eroded the further you go away. And so people, when they were first looking at this, had no idea that the Earth was moving, that big sections of the Earth's crust move. So the original idea was, and I forget, John, I don't know if you remember, was it Dana or somebody who said it was like a whole line of candles. The volcanic chain was like a line of candles that have been snuffed out from the north one at a time. And so leaving only the southern end ones active. You know, so the reverse of that is actually really what we're looking at. Instead of them going extinct from the north and coming to the south, is they're active at the south, right, when they pass over the hot spot, and then the Pacific plate is moving off to the northwest like this, and it's carrying these other islands away like conveyor belts. So we're sitting on a hot spot, we're melting stuff, and when you're right on top of the hot spot, we get lots of melting. As we move off, the amount of melting decreases, and also the place where the magma is stored moves down back inside the crust and down into the upper mantle, because it has to, it's a smaller amount of melt, so it has to stay deeper to stay warm without solidifying. So when you're right over the hot spot, those magma chambers are shallow. They're only like about 1.5 miles, 2 miles down below the summit of Kilauea. When you see the magma that's up at the surface, it's coming from a much bigger magma chamber down there. One of the things that when you do move off and you kind of drop the amount of melting, so it's lower amount of melting, and store the stuff deeper in the earth, you get a different chemistry. And so if you've ever looked at Mauna Loa and Maunakea, anybody ever looked at Mauna Loa and Maunakea? Never seen them. Okay, well, next time it's sunny, go right outside this building. Actually, UCB, the building on the other side of campus, if you go to one side of the elevator, you can see Mauna Loa real well on a clear day, and the other side of the elevator, you can see Maunakea real well on a clear day. So it's got really great views of the two. What's the difference between them? What's the most noticeable thing about one's what? One's better. Well, aren't we judgmental tonight? That's true. One always has to be better. It's an unwritten rule. I believe there's someone in the audience here that told me tonight that the happiness of one child is directly proportional to the unhappiness of the other. So one is better, but besides that, why do they look different? What's different looking about them without being too judgmental? Smooth and bumpy, exactly. So they're smooth and bumpy. And that's the chemistry of the lava that's making one smooth and one bumpy. Right? One has stickier lava and one has more fluid lava, and it's because of this melting process as you move off the hot spot. And so we get volcanism going back about to where Oahu is right now. And then after that, it kind of turns off out in there. So, and those are the kind of things like the Diamond Head is that kind of volcanism. It's probably about 200,000 years old, something like that, 150,000 years old. We're not really exactly sure on the exact date. But so there's been some volcanism back on Oahu. When you get over to Kauai, the volcanism is more like the last volcanism was about 500,000 years ago or something. So we get that deep stuff that's there, and that deep stuff that comes out actually brings up pieces of the mantle with it. So like Salt Lake Crater is a place that we can find pieces of the deep inside of the earth brought up with the volcanic eruptions. So this is a picture of global hotspots, And so there's lots of little circles on here and big areas where lava has come out of the ground. And so this is kind of all the hot spots. And here's the Hawaiian Islands right out in here. And so they're in the deepest part of the Pacific out here. And if you look at them out in here, here's the main part of the Hawaiian Islands. They also go up this way as part of the Emperor Seamount chain, but we're just going to look at this. And notice that the seafloor around them, in these lighter colors, is higher or not as deep. And in the dark colors in here, that's the deeper part of the seafloor. This is a result of two things. One is moving over the hot spot, and it heats the crust up, so it kind of arches up. And the other thing is the weight of the volcanoes themselves have kind of squished the crust down. It's kind of like bending a board underneath them. And so you can see on either side, we have things that we call the arch on this side, the arch on this side. And then there's kind of a trough that runs around them. Most of the trough out in here is filled in with stuff that's eroded off the island, so you don't see it as well. So here's another picture of, oops, hit the wrong button. Here's another picture. Here's the main Hawaiian Islands back to Kauai right here. And then here's the Northwest Hawaiian Islands and the Emperor Seamount chain going all the way up in here, where then it's pulled back into the interior of the earth where the Pacific crust goes in along the Kurau Trench and the Aleutian Trench right in there. So this is about 80 million years of history. It's about roughly 42 million or something like that from here to here, and another 40 million or so going off in this direction. So we know the hotspot's been around for at least 80 million years, and then the rest of the record is pulled back into the interior of the earth. So we're not sure how long it's been here in total, but a long time anyways. And this is showing the main Hawaiian Islands, Kauai, Oahu, Maui, the Big Island, and I've kind of put a circle on here, kind of overlapping where the main part of the hotspot is in here. And it's sitting, we've got Mauna Loa, Kilauea, and Loihi kind of sitting within that hotspot ring out in there. And if we look at this, Loihi, we're not too sure, probably erupting. It's just coming onto the hotspot, and we're probably decades between eruptions there. On Kilauea, it's kind of years between eruptions or continuous eruptions, right? Mauna Loa is kind of decades between eruptions. Hualalai over here is centuries. This is millennia, and this is, last eruption was about 120,000 years ago on Kohala. So as we move off, what we're seeing is the eruptive activity is decreasing, the span of time between them is increasing, right? And we get over and we do get this, what we call rejuvenated volcanism. So like on Haleakala, if you go up to the crater, there's a whole bunch of young looking cinder cones up there. They're about 500 years old. So this is what we call the rejuvenated phase of volcanism. And Hawaiians undoubtedly saw those eruptions. I mean, they're up there. They would have seen them from anywhere pretty much on Maui. So a couple things that we'll look at as we go through here is, here's this deep part in purple around the islands right in here. Here's the islands. Notice that the islands out in here have a very big underwater kind of base. And really what these are old shorelines. So Maui, if you want, kind of was like this size of an object when it was active and on the hotspot. It was a much bigger island than it is today. And then we also can see things like this. That's a piece of Oahu that came from over here, right? And so that piece of Oahu, you could drop it in the greater Honolulu area and obliterate it. That would end our problem with light rail, but but anyway, those are big chunks of the island that have gone off on the seafloor, both from Molokai and from Oahu. And there's lots of stuff, like this is a big slide off the Waianae coast in there. And you can see all the debris that's coming off of Kauai over in here. So the volcanoes fall apart. They're really a kind of a slapdash construction project. They're built up really rapidly because they build within 1 million or 2 million years. And they're built on a bunch of black sand, basically, and big round pillow lavas. A friend of mine called them like, it's built on watermelons and ball bearings. So they're kind of sitting there, and then we put the big volcano that looks like real rock up on the surface of it, but it's sitting on an unstable base. So they tend to decay in size as you move off of the hotspot, and they're not active anymore. So they erode, they fall apart, and so the islands get smaller and smaller as we move up to the northwest. Here is a use of, this is actually using gravity and looking at the mass of the volcanoes along the chain. So here's the main part of the Hawaiian Islands. This is out a little bit past French Frigate Shoals, out in the northwest Hawaiian Islands. And then this is the Emperor's Seamounts out in here. And what they're using is they're looking at the interior dense mass of material that's been added to the crust in there. And what they're getting is an eruption rate. So right now, what we're producing at Kilauea is about 2 cubic meters per second, right? And so what they did was change this gravitational mass into that same thing. So if we look right in here at the total output over our island of Hawaii, and this is with Mauna Loa, Kilauea, Waialae all together, we're looking at something like 6 to 8 cubic meters per second. We had another big area out over in this area, you know, back around 20 million years ago, where there was another big volcanic platform. And what it shows is that the output of the hotspot varies with time, right? And we're at a high output time period right now. And then we've had low output periods as well. And particularly, let's go back and take a look at this. If we look right in here, after the bend right in here, none of these volcanoes made the surface out in this area. So there was a period of about 15 million years where no volcanoes made the surface in there. So we know that the output has varied over time. We can see it by the mass of them, of the different volcanic islands, but this is a better way of doing it to get the actual amount of lava coming out. Oh, sorry, these are, doesn't everybody read geologies? This little thing that says Ma isn't your mother, okay? That's millennia. Sorry about that. Thank you very much for pointing that out. That's just a little oversight there. So the little Ma is millennia, so it's thousands of years. Oh, sorry, millions of years. Sorry. I'm getting my head shook out. Yeah, so these are millions of years, 20 million years, 30 million years, 40, 50, 60, 70. So the age of the chain right here. And the other thing is that there's families. These guys cluster in families. So we're going to get into the whole sibling thing. There's also family rivalries as we go down the chain. And so if we look at these things, oops, we've got these two different trends that we can do. And this isn't just a little game, you know, that you played where you connect the things and you can draw a rabbit on Easter, right? You connect all little dots. So it is kind of like that. Is connect the dots along the volcanoes, right? And they connect into these chains. And okay, so you can do that. We can draw a line through them. That sounds like something a geologist would do. Yeah, it is. So we had to get some chemists, and the chemists came in and they looked at these things. And what it is if we look at the lavas that were produced from these volcanoes when they were on top of the hotspot, if you're along this line, you can't tell the difference chemically between those lavas that were produced along that line. So they're all one chemical family. And so same thing on this side. So we have this Loa trend over here named after Mon Aloha, right? And so these guys are chemically different and they're all the same. We have to pick up the same stuff that was produced right here, right? So we can tell those kind of, these are things called foliite lavas. And so we look at those. So we have these two different flavors, which is interesting. This will come into play because I can't tell you, if I'm looking at the older part of Kohala Volcano, I can't tell you the difference between that and Maunakea Volcano chemically.
What about up there where the lines aren't extended? We have those red lines.
Okay, those are more volcano locations right in here. So the Loa trend would kind of go out that way. And in some places, there's, if you go along the island, along the northwest Hawaiian Islands, some places there's 4 of these tracks parallel to each other out in there. So there's a lot of them. They're continuous, and they have this kind of chemical composition that stays continuous. I wish I could tell you more about that. It's one of these things, like I was talking about, that's screaming something at us, and we're not sure. It's telling us something fundamental about the kind of plume of the hotspot as it comes up underneath the crust, but that it can make kind of a constant chemical composition, and we're talking about for about 2.5, 3 million years out to this point in here. So why it does that, and then they stay consistently different right next to each other. So if you pick up a piece of Mauna Loa and a piece of Maunakea or Kilauea, I can tell the difference between Mauna Loa and Kilauea. We have a machine. Steve there has a little machine in his lab. We can put the rock on and instantly tell you which one of those volcanoes it came from. But I can't do the same thing along the trend, right? We can't tell them apart along the trend. But between the trends, it's really easy to tell them. And it's a kind of a mystery, but we can leverage that to be able to tell, you know, which side of the trend rocks came off of. So Hawaiian volcanoes all have to start on the seafloor. This is another geology thing, duh. They start off small and they get big, okay? Everybody got that? You want me to repeat it? Small, get big. Okay. See, you guys could all be geologists too. Okay, so we have to do some things though. Like I'm actually a petrologist, which petrologist from petro, rock, right, in Greek. And so if you actually un-Greekified my career name, it's called rockologist, which just really, how many of you guys would have come tonight if you knew that there was a rockologist that was talking? Yeah, we get a little sketchy there, right? Sound system, yeah. Instead of my outside voice. So they start on the seafloor like Loihi. They're small. Loihi is, you know, people say, well, it's only 3,000 feet below the surface. And it is only 3,000 feet below the surface. But they have to build like a pyramid, right? So that 3,000 feet means Loihi has to get about 10 times bigger than it is right now to break the surface. So it's going to be a while. So if you were planning on renting a boat and camping out over that so you could get some cheap Hawaiian property, when it comes up, it's going to be another, 100, 200,000 years before that thing breaks the surface. So don't waste your time right now. So as these guys build up, they break the surface and they go into what we call the shield building stage. And so Mauna Loa is the classic kind of shield, and it looks like a Roman wire shield just laid down on the ground, right? You could call it a bread bowl volcano, but that wouldn't sound very good, right? Because it looks like a bowl. But shield sounds much better, right, when we do that. So we just use names like that. And what you can see on the picture over in here is the shield part of the volcano, the part that actually erupted when the thing was above the surface, is actually a kind of a small wedge. And then it's sitting on all this stuff, which are these pillow lavas and sand. So these kind of bulbarians and watermelons. So the base of the volcano is pretty unstable. And you've kind of seen that process if you've been out to the ocean entries. You've seen that process in action. You talk about benches collapsing and things like that. That's the small scale version of this thing that happens to the whole island, right? The entire island is built on that stuff that is not very stable underwater. So these guys oftentimes have calderas on them. So Mokuaweoweo caldera and Kilauea caldera, and that's because the magma chamber is up high in the volcano and is very active, right? So we have to pass a lot of magma through there to keep it hot. And so this is really unusual. Most volcanoes don't have their magma chamber up inside the volcano. If you go to Mount Rainier or something like that, the magma chamber is like 8 kilometers down in the crust. The volcano is just a pile of stuff that's been spurted out when the magma chamber leaks to the surface. In Hawaiian volcanoes, they build, and so here's the Loihi size thing. As they build, the magma chamber rises with the volcano. And so it stays in the interior of the volcano. The only way that can work is that we're pumping a tremendous amount of lava through. So there can be all sorts of arguments about where the world's most active volcanoes are and stuff like that, like because Stromboli, there's a record of activity there for about 2,000 years. Vanuatu, it's almost always active and stuff. A lot of those volcanoes aren't producing much in volume. Our volcanoes, whatever you want to say about, temporal activity, our volcanoes by volume of lava produced just dwarf any of the other volcanoes on the planet, really, in terms of how much stuff comes out of these guys, on a yearly basis. They're really, really productive. And then as we move off, here's the shield stage under here. The magma chambers go back down into the crust, and we get this alkalic lava that's stickier, and we make these cinder cones, and it kind of makes this cap. And because it's stickier, it makes a steeper top. And Mauna Kea, I think most people think looks more like a volcano than Mauna Loa because it's got the pointy thing that we're used to. And even everybody that's grown up here in Hawaii, if I ask them to go draw a volcano on the board, guess what they draw? They draw a little triangle instead of an arc, right? But our volcanoes really look like an arc, right? They're smooth like that. So this thing is grown up, and you can see the eruptions are much stickier. The material comes out more as particles. A lot of it cools, and that's what makes a cinder cone, right? When you have that kind of eruption. So here are the volcanoes in the crater at Haleakala. So these cinder cones that cut across here are about 500 years old, and they've produced a lot of lava that's filled in these big erosional valleys. So what we have in here is someplace where the alkalic cap starts to erode, and then material gets filled in. So here's Kohala Volcano, where we see this kind of erosion. on the north side of our island. And another thing that's very interesting about tropical erosion, that normally you think, where does streams start? They start up at the top of the mountain and they start eroding from there, and that's where the valley starts, right? So really here, what happens is the valleys actually start right at the coast. You can see this one. It's kind of like sawing a piece of wood. You notch the edge of the piece of the wood. So when the water starts cutting a little notch in here, that's where the erosion starts, and it cuts backward. So like Waipio Valley has been cutting backward like this, and so it's trying to get to the top of the volcano, so to the top of Kohala Volcano. It's not there yet. If it ever does, it'll do what happened here on Haleakala, where the Kenai Gap and the Kaupo Gap both came together. They were big headward cutting valleys, came together and took the top of the mountain off. So this crater is not a volcanic crater, it's an erosional crater, and then that localized trapped all the subsequent eruptions inside, which then started filling it up again. So it's kind of a weird history in there. And then as you move out, the volcanoes get smaller and smaller, right, until they're just kind of rocks out in here at Necker and Nihoa Islands, and then they form little atolls where they're capped by coral, and then finally they're going to go underwater, and they're going to become what we call seamounts. And so we have that long chain. About half of the Hawaiian volcanoes are in the Emperor Seamount chain. And so how do we know they were ever at the surface? Well, we've run dredges and drilled on them and stuff, and you pick up corals that were shallow water corals off the top of them. So there's no doubt that they were there. And you know, all the way up to almost in the Aleutians, you can find corals on top of these volcanoes down at the bottom of the ocean now. So that's kind of the history. So we kind of know how these things evolve as we move off. So there's slightly different behaviors of the volcanoes. We'll come back down here. So now we're going to come back to this question right in here. Is Mauna Kea the world's tallest mountain? And to quote somebody famous, I guess this was roughly paraphrase, I guess is more it. It depends on what the definition of is. Yeah, it's sort of like that. So we have these two volcanoes, right? So we have Mauna Loa, Mauna Kea. We're talking about which one is taller. This one's 13,800 feet. This one's 13,700 feet. Okay, that's not how tall they are though, right? What's that?
That's down to water.
That's down to water. It's elevation. It's how high they are, right? So Mount Everest is up close to 30,000 feet, right? So it's way higher than any Hawaiian volcano. Now the question is how tall they are, right? From their base to their top. Okay, then we're looking at tall. Like if we stacked a bunch of people, that's what we'd be looking at. So it wouldn't matter if I took a small person and put them on the table and they were higher than me, it doesn't mean they're taller than me, right? So that's the definition a lot of people are working with, and Wikipedia uses that definition to make Mauna Kea the world's tallest volcano. Okay, so it goes from about 18,000, a little shy of 19,000 feet, plus 13,000 feet. It's about somewhere on the order of 32, 33,000 feet, depends on where you measure it from. And so here's a topographic map of the submarine part of the volcanoes in here. Here's Mauna Kea, and so what they're doing is measuring from this point way down in here, which is a fairly deep part of the trench right in here, and it's about 5,700 meters, and measuring up to the top right there. So that's where you get that to be the world's tallest volcano, or is it? Depends on what is. Like, where do we measure these things from, right? So Mauna Loa is 100 feet shy, and the deep over in here, on this side, it's all been filled in with gigantic landslides that came off Mauna Loa. On this side, we haven't bent the crust down as much because the island is just growing over it right in here. So over on this side, the crust is bent at a steeper angle underneath the islands, and so we have a little bit deeper place in there. But we're going to go investigate some things. So one thing you can see in here, here's Kohala Volcano right here, Mauna Kea Volcano and its submarine rift zone. And here's Kilauea's submarine rift zone that goes up like this. So Kilauea is a very long volcano. And Mauna Loa kind of comes from here and goes out to its submarine rift zone like that. So we have these volcanoes, and they're kind of stuck together like this, right? So it's like you put a bunch of things together and they grow against each other. If they weren't stuck together, they'd make kind of just sort of like pancake shapes, right? They would be symmetrical and circular in plan form, and all the lava would come out either the central crater, or it would come out in like radial, what we call dikes or fissures, that they radiate out from the central part. On our volcanoes, the magma comes up underneath a caldera, and you can see it good on Mauna Loa right in here, goes down these longitudinal cracks that we call rift zones and comes out from those. So our volcanoes, we have these very well-defined spots out in here where lava comes out that we call rift zones. The main magma chamber is underneath the caldera. On Mauna Loa, there's another trick that it's pulled out of its bag as well, which is on the north side and over to the west side. Notice this is the 1859 eruption right in here that goes down by the Hilton Waikoloa, just a little bit to the south of it. And that came out of a vent that we call a radial vent. There's some vents that just come out of the flank of the volcano out there. And that's allowed Mauna Loa to kind of cheat a little bit. I mean, Mauna Kea really kind of, its lavas cover this area and down over into here. But Mauna Loa flows have kind of come over onto this side of Hualalai. They wouldn't normally make it over there very much, but these little kind of radial vents over in here have allowed it to sneak down in here. So this is covered by Mauna Loa, this little section in there. So just even on the surface, it gets a little bit hard. What is Mauna Loa volcano? What is Kilauea volcano? What is Mauna Kea volcano? We can look at the surface lavas and identify them by their lava flows that belong to them, which means Kohala is about right here, right? And Mauna Kea is kind of over in here. Mauna Loa has a weird pattern where it comes down here. Then Hualalai is kind of sticking up out of it, comes around here and comes over here. Kilauea is this little chunk over like that, right? But we don't really see inside of them to see what they're like. But we know that like Mauna Loa is older than Kilauea. So Kilauea is actually kind of sitting on the knee of Mauna Loa. So it's actually sitting there. So it's a little bit taller than it should be, a little bit higher than it should be, because it's sitting on Mauna Loa's lap when it started to grow. And Loihi is doing that, right? It's off on the flanks of Kilauea and Mauna Loa, right down in here. So it's kind of sitting on the side and building out on the side of these other volcanoes, which will continue to grow as well as it grows, right? So it's a complicated relationship. If you want simple, go to the Galapagos. They actually have simple volcanoes that are separated, and they also have simple evolutionary trends and all that kind of stuff. It was all done 150 years ago, right? So it was all taken care of. So go there if you want to see this, and like just there's all volcanoes are separate. They have their own identities. Here in Hawaii, we have this much more complicated relationship with our volcanoes. So here is the island looking at it from Google Earth in here. And so, oops, keep missing that button. There's Mauna Kea, Mauna Loa out in here, Kohala Volcano. Here's the point of Kohala Volcano out in here. Hilo's right down in here. Here's the submarine rift zone that's always been attributed to Mauna Kea Volcano. And then here's the submarine rift zone of Kilauea Volcano out in here. So what you can see is that the subaerial part of our volcano is it's not nearly as massive as the submarine part in here. And the submarine part has a very steep drop off. The rift zones are very narrow. But notice this thing right in here, this big blue part right in there. That is an old shoreline of Mauna Kea Volcano. So Mauna Kea Volcano is actually bigger than we're looking at it. It actually extended out to here. And what happens in the tholeiitic shield stage is the eruptions are so fast that we can never build reefs or something. Whenever there's any little edge built on the ocean there, lava goes in and just covers it up and adds it to the volcano. So as soon as it moves off into the stage, the alkalic stage that Mauna Kea is in, then what happens is we're not producing nearly as much lava. And so these volcanoes are sinking. We're sinking at about 2 to 3 millimeters a year. And so they sink into the ocean. And you think 2 to 3 millimeters a year, that's no big deal. You'd still take a house along the ocean, wouldn't you? How many people would reject a house on the ocean because it's sinking 2 to 3 millimeters? The one person back there, okay. The rest of us, sure, I'll take the nice beach house. Why not? You know, we'll take it, you know. Yeah, you want one? Uh-huh.
And I learned all about this.
About the island sinking?
Like, I did this already.
Oh, well, this is boring then, so we should just move on then. Okay. You sure you don't want to do the math again? We're at about 100 feet sea level, okay? At 3 millimeters a year, how long before the beach comes up to us? There, you can work on that.
Oh, yeah.
Oh, yeah, actually we do. We'll talk about that in a minute, too. because it's not the first time that we've been to that rodeo. No, sirree. We've been to the sea level rise rodeo before here on our planet Earth. And we're going to talk about it right now, actually. So here's another map showing the part of the island that's exposed is in gray here, because it's not interesting. I'm just kind of like, yeah. And we're looking at Maunakea going out this way, Kilauea over here, Maunaloa over here, and Kohala over in here. Notice with the coloration on here, you can see what looks like a whole series of steps coming off of Kohala Volcano. Look at those. And there's one other volcano, Maunakea Volcano, right in here, which is the oldest volcano, and it never breached the surface. So we've got these steps, and you can kind of, the old shoreline of Maunakea is over here. This is the old shoreline of Kohala Volcano over in here. It's about 1,200 meters or close to 4,000 feet deep now. So those little 3 millimeters of year add up if you give it a little time. Like way down there, right? 4,000 feet below sea level. The stuff that was at sea level, right at the coastline there, is now 4,000 feet down. Right? So we're sinking a lot, right, over time. So we look at this guy out in here. We have all these little ridges right in here. And so I'm going to show you a picture of another. Most of this stuff was done by sonar, the bathymetry in here. And this is some stuff that was done by MBARI, the Monterey Bay Aquarium Research Institute. And so what they did was they did sonar out in here, and then they did dives on all these old reefs. And they collected corals. And we can date the corals because certain species of corals take up a tiny amount of uranium out of the water. And it allows us to use the kind of decay clock in the uranium to get dates on it. So now it's back to a Jeopardy question right in here. Okay, dates for 500. What are these ages? They're in thousands, they're in hundreds of thousands of years, right? So they're in 350,000 years, 250,000 years. Yeah, but what great moments in geologic history do these represent?
Ice Age.
What part of the Ice Age? They do represent ice ages. I don't know. These represent the ends of the big ice age states. And what happens is these are huge coral reefs. Do we have a coral reef like this that goes for miles around our island now? No, like in the middle of the ice ages, we had gigantic coral reefs fringing our island. Right? They're huge. So we had skiing all year round on top of Maunakea. And then we have these giant coral reefs you can go snorkeling. And we have a plentiful abundance of Canadians because their country's under about a mile of ice. So we'd have lots of people to come here and visit. But we have these giant reefs going around. And the reason is that our island is sinking this 3 millimeters a year, which is too fast for the big corals to grow. They get drowned. And so we don't establish these big reefs. But when an ice age starts, then slowly the ocean level is going down, and it drops to about 300 feet below present-day ocean levels. So it goes down a lot, and it goes down very slowly because it takes a while, because that's basically snowing on Canada, right? So we have to take that out, snow on Canada, snow some more on Canada, snow some more on Canada. So the sea level drops very, very slowly, and the coral reefs grow during that period. At the end, when the ice caps melt, it happens really fast. Within about 1,000 years, a large part of the ice cap decays, and within a couple thousand years, it's all gone. So sea level rises real quickly after that, and it drowns these reefs. So what it does is we preserve the last growing guys on these things, and here we have the ends of the major ice ages, right? So this is kind of like looking for the last 500,000 years, ice ages in here. This one is at about 1,100 to 1,200 feet down. And I'll show you, I've got them marked on a Google Earth thing here. You guys can see all the reefs on that, right? Not quite as nice as this, right? But that 400,000 year reef is right here, right? And then we have the 125,000 year reef right up in there, and we'll put those on them. So there's the reefs in the green and blues. And then the old shoreline of Kohala Volcano is right in here, right? And then this is Maunakea Volcano right down in here. And what you can see is that the shield of Kohala Volcano grew on top of Maunakea Volcano. And so at one point, Maunakea was almost at the surface, but not quite. And then Kohala grew. And so Kohala Volcano is really a big thing, right? It was huge, right, out in this direction out in here. There's Maunakea Volcano, Maunaloa Volcano out in there. And so we look at these guys, and then we can go around. Here's kind of coming around and looking along Kohala Volcano. And I want you to just get a look at this kind of shape. It's kind of long and narrow. It's like a whale's back coming up. So if you've ever seen a whale kind of come to the surface, you're seeing just that part of its back. And that's what Kohala is like. You're seeing the back of that volcano coming to the surface of a much, much bigger thing. So it's coming up over like this, and then it dives somewhere underneath Maunakea Volcano, right? We don't know where. And then, so this is the old part of Kohala Volcano, and then the shoreline of Maunakea Volcano starts over here in Waipio Valley and stuff over in there. This is coming around Hilo side. So Hilo's right in here. This is Hilo Bay. This is the submarine ridge that we call the Hilo Ridge that we've always thought belonged to Maunakea, which is right there. So here's Maunakea coming down to the shoreline. Here is Maunakea's old shoreline out here. So you kind of see it. And then, remember I was talking about there was a little weird thing. This is that little weird thing right here. There's a little weird bench right here. This is at about 800 meters. This one right in here is at about 11 or 1,200 meters. It's right about where the shoreline of Kohala is on the other side. That's a little piece of Kohala's shoreline right there. And it took a while. People noticed that. Robin noticed this probably, do you remember like early 90s maybe, John, or something like that, that he noticed this little piece? And then people started working on it, trying to figure out, wow, can we actually prove this? That, you know, Robin just said, well, I think Kohala Volcano goes all the way from Kohala all the way out here and down to the Hilo Ridge. And everyone went, yeah. You know. But then he said, look at this little thing out here. And it makes sense when you look at the logic of it. And this was at the same time, all of these things about the reefs were just being kind of figured out. So it took a while. Robin did this before we had the ages of the reefs and the subsidence rate down very well and stuff like that. So he had a really good, you know, sense of this, that there's something weird right there. And it's just that little thing. How many people would have looked at that little thing and gone, wow, what is that? No, all of us would have gone, well, there's the shield stage of that, and there's the submarine rift zone. Okay, it's all Mauna Kea, fine, good, bye. You know. Now the trick is, remember, is if this is really Kohala's submarine ridge, we can't pick up a rock of this and tell the difference between the shield stage part of Mauna Kea from the shield stage part of Kohala. So we can't pull the chemistry trick because they're in the same chemical family. So there's no easy way to do that. So here it is looking at these guys. Here's the Mauna Kea shoreline. There's the Kohala shoreline, the little teeny bit sticking there. And then here's this submarine ridge. So how can we do this? How can we figure this out? Isn't everybody worried and concerned now? Like, how can I ever go home and sleep again without thinking about this all night long? No, it's not really a problem. You'll be able to sleep after all? Okay, well, maybe it's just me that goes home and worries about these things. So if we take those subsidence rates, okay, and we look at these guys in here, what we're looking at in here is these contours. Here's the island of Hawaii, Maui, Oahu, Kauai right in there. And what these contours are is looking at the depth of the seafloor. And the depth of the seafloor down in here goes down to over 9 kilometers beneath the ocean surface. Now, the depth of the seafloor out in here is really about 5 kilometers. So that's an extra 4 or 5 kilometers that the seafloor is bent down under our island. So now we're doing, remember we talked about what is in terms of how tall something is? Now we're talking about where is the deepest part of the ocean crust? Well, it's right underneath the islands. They've bowed it down, right? So which one of these guys is really the tallest volcano after all? Right? Because it depends on where we measure it. And how tall are they? Are they a mere 33,000 feet tall, for example? Or are they even taller, right? And so this kind of thing suggests that they're a little bit taller than that. And we also have, this is data from a drill hole that was drilled right by the airport. So here is Pane'eva over in here. Hilo Bay is in this little white thing right here. Hilo Town right there. And the drill hole is right there. It's actually, as you go into the airport, it's off on the right across from the National Guard. There's nothing there really. There's a pipe in the ground. But it drilled about 3 kilometers or about 11,000 feet into the island to just see what the structure was and see how far they were going through Mauna Kea. And this is what they got. So they start off at the surface right in here. There's Mauna Loa flows on top, a fairly thin bit of Mauna Loa flows in here. And then right about here, about 100,000 years ago, then we get the kind of these alkalic capping flows from Mauna Kea that are all surface. And at 400,000 years ago, we start seeing submarine material in here and all the way to the bottom of the hole, which is about 650,000 years old. So we get this idea. So that's 11,000 feet or 2 miles of the volcano that are underneath Hilo Airport. We never got to the crust, right? So we're not even really down to seafloor depth, because this is 11,000 feet. Seafloor depth out there is about 18,000 feet. So it's hard to drill. The drill, they were trying to drill deeper, but they couldn't get any deeper because the drill hole collapsed and stuff at that depth. So problems with all that kind of stuff. But anyway, this is probably all Mauna Kea. But at some point, they might have gone into Kohala, but we'd never really know because the chemistry isn't different. So we never really know when we're hitting submarine lavas from Mauna Kea versus submarine lavas from Kohala. So that was expensive and didn't solve anything. So let's go try something else. This is the map my friend Jim made. If you guys know Jim Koikawa, who was, for 10 years, he was the scientist in charge of the Hawaiian Volcano Observatory. And for 20 years before that, he made this map. That's what he did. And this is a gravity map. Everybody like gravity maps? You make your own gravity map. All you need is a gravimeter, which is a little teeny weight on a little teeny spring. And basically, that little teeny thing measures how strong gravity is. So if we look at this, the colors in here show if they're more red and yellows, they're higher gravity. And then if they're blues, they're lower gravity. So here's the outline of the big island right through here. And here's Hilo. And if you notice, we're in a gravity low. So when you're down here, gravity isn't pulling you as much. So you have a lot of spring to your step. If you're old like me, you feel really good. If you go to the top of Mauna Loa, gravity is very high. And you get up there and you feel like crud. And you can barely move. You go, oh. Because of the high gravity, right? Anybody notice that? Anybody been to the top of Mauna Loa? Don't you feel that way? It's just hard to move. You can't do anything, right? That's that strong gravity.
And it makes the internet connection unstable.
The gravity does?
Yeah, that's what it says.
Oh, well, that's Fritz's thing. I don't know what it's doing. He's like doing some Facebook thing or something like that. I don't know. But so gravity, well, these are in milligals, like in thousandths of a unit of gravity. So they're not very much gravity. So I'm lying, maybe just exaggerating a little bit, just a wee bit. But the gravity is higher, and this is with the effects of topography taken out. So what we're doing is looking at the mass inside the volcanoes. And so our volcanoes have a lot of the mineral. What mineral is it? No geologist can answer. You guys don't try and act too smart. What mineral do we have that our volcanoes got lots of? Silica. That's an element. Oh. Yeah, you're doing the Captain Crunch form of minerals. If you look on the back, you can have sodium, potassium. Those are not minerals. Those are elements, okay? Oh, you got one? Iron is an element too.
Mountains?
Mountains, is that a mineral?
Probably not.
Probably not. That one is a little too big for a mineral, but somebody said it earlier. Olivine, yeah, olivine, the little green mineral, right? So we have lots of that. The olivine is heavier than the magma, so it sinks out of the magma. So the cores of the inside of our volcanoes have large piles of olivine in them. And they show up as these big gravity highs. So here's Kilauea. There's the summit right there. These little black squares in here are vents along its rift zone. And you can see it's underlain by a giant gravity high that goes out. And then they put all the, I don't know why Jim did this, but he put all the landslides on this to obscure everything. Well, it's actually, I know why he did this, because he didn't have good data out there. That was all done by somebody on a ship. This was all done by Jim and his assistants on land. And oh my God, is it a pain in the rear end. He would just sit there. They had to go calibrate their gravimeter, keep it at a certain temperature. They'd go out and make 2 measurements, come back to their calibration station, make 2 more measurements, and call it a day. And then he had to spend about 20 years till he got the like 5,000 measurements it took to make this map. Going all over the island, right? And so he has really good data on the island for this precise gravity, and it's not so good off of there. But you can see the rift zone. Here's Mon Aloha, and these are the vents, all the little black guys in there. And so you can see the rift zone, and here's the summit caldera in here where gravity is the highest. And then look at Mauna Kea. All these purple things are the vents on Mauna Kea. It looks kind of like you just shot a shotgun at it, right? Just blast it in there. And its gravity high is kind of right underneath the summit of it, and it doesn't go anywhere. And then if we look over at Kohala Volcano, here's its vents, It's covered by Mauna Loa or Maunakea lavas from here on over, but look at the connection of the gravity high that goes over through there. So the gravity is seen through the lava that's sitting on top of it and seeing this elongated structure that goes over and connects with that little teeny itsy bitsy thing at 1,100, 1,200 meters down, that little bench over in there. And so what we're seeing is that the submarine part of, we go back to this guy right in here, there's a gravity high connecting this all the way over in here. And that's why I called like this part of Kohala just kind of the back of a whale, the deep part of the whale. It comes all the way over in here, all the way down in here. So it looks like we have this one massive long volcano that cuts across all that, and Mauna Kea is just sort of perched on top of it. So is Mauna Kea more like the little kid I sat on the table now? And it's sitting on Kohala Volcano? Is it cheating just a little bit? Nancy, you know about that, don't you? You're already tall. You don't need to stand on the table and cheat. Okay, you're already taller than anybody in the room. So this is where it gets a little tricky, right, when we're trying to decide. And here is a comparison, and oh, the blue doesn't show up very well. But this is Haleakala. And Haleakala has a ridge that goes way out like this with a rift zone. The subaerial part, here's the part that's above water right now of Haleakala. And this is the old edge of the shield down in here, and then the submarine part. So it has the longest rift zone that we know of here. It's on the order of about 70 miles, 80 miles. No, it's longer than that, probably 100 miles long. And if you bring it up and place it over the Hilo Ridge, over to Kohala Volcano, it's not as long as the rift zone of Kohala, which is shown in blue right in here. So if this is with the Hilo Ridge, really belongs to Kohala Volcano, it goes all the way there. So it makes Mauna Kea just look kind of like a little thing that's sitting on the side of Kohala Volcano. You're going, look how tall I am, look at me. So it's a little bit hard to know, but the one thing that's interesting here is this shotgun pattern. Usually these guys are following the weakness in the volcano, which is the rift zone in here. And so Kohalas follow that. Mauna Kea doesn't actually show a real rift zone preference. It doesn't show a direction in it. It looks like it was more like a Galapagos volcano, more circular planform with cinder cones that could just erupt anywhere along it. No elongate direction and rift zone in it. So here is kind of the size of Kohala Volcano reconstructed in the blue right in here with its rift zone. And Mauna Kea Volcano is just kind of sitting on top of it, covering part of it, right? So it's really this blue thing in here. So now Mauna Kea is looking like it's just sitting on that. Now, Mauna Loa is partly on top of Mauna Kea as well, right? So it's kind of like a wedge going underneath it over in there. And here's Kilauea's rift zone, Mauna Loa's rift zone out in there. And this is a little picture right in here showing here's Kohala Volcano. That's what's left of Mauna Kea Volcano, that wedge right in here, and then Mauna Loa Volcano and Walleye Volcano going off that way. So now it just doesn't look quite as impressive as it used to. Now you're going to be looking outside and you're going to look at Mauna Kea the next time you see it come out and you go, oh, that jerk ruined this for me. I used to think that was a really tall, nice mountain, and now I just like look at it and go, oh, it's just a wedge of stuff up there. Right? So I'm sorry I just spoiled the whole island for you, but that's the way it is. So if we look at these guys, here's Mauna Loa Volcano. And just to give you an idea of how big these guys are, this is Mauna Loa, the size of it, and here is Mount Rainier by comparison. Right, though. So if you've been to Seattle and looked at Mount Rainier looks a whole lot bigger and more terrifying than Mauna Loa does, right? But when you actually measure it, Mount Rainier is built from about 3,000 to 4,000 feet above sea level. That's where the old rock is. So it goes up to 15,000 feet high. So it's really about 12,000 foot high volcano. And if we measure this guy just to the seafloor, right, we're looking at 13,000 feet plus 18,000 feet. So somewhere on the order of 31,000 feet high for Mauna Loa. And then if we count how far down the seafloor is bent underneath it, we're looking at a volcano that's really about 45,000 feet, right? That's a lot of lava in there. And so these guys are really, they're unfathomably big. So here is kind of a picture of, there's Mauna Loa, and you can kind of see here's the submarine part of it bent down. Here's the ocean crust bent down. So there's this big, thick wedge of stuff underneath these volcanoes. So we have the subaerial part, we have the submarine part, and it's all bent down. And this is like 45,000 feet of material in there.
I don't understand the difference between subaerial and submarine.
Subaerial is the stuff that's erupted when it was above sea level. Submarine erupted when it was below sea level. So subaerial makes the smooth, hard lava that we're used to, and then the submarine stuff are these pillow lavas and black sand. They're kind of what's underneath the benches that are out in the park. Or if you've seen the black sand beaches and stuff, that's basically what they're made out of underneath there. Sorry about that. I should have explained that earlier on. This talk would have been a lot more easy to understand, wouldn't it? Should I just go back and we'll start over? There's going to be a lot to edit out of this. You're going to be very, very busy, Fritz. So here is the revised volumes in here. And unfortunately, that thing is on top in here. But this is volumes in terms of thousands of cubic kilometers of material. So Mauna Loa, we used to think was about 70,000 cubic kilometers. Now we think is about 95,000. Mauna Kea is way down here on the list. 1, 2, 3, 4, number 5 on the list of big Hawaiian volcanoes. It got a big demotion in its size in there. So it's only on the order of about 41,000 cubic kilometers. How much is a cubic kilometer? It's a lot. Yeah, we'll just measure it in a lot. Yeah, it's a lot of stuff in one. 3,000 feet by 3,000 feet on the side, right? So it's a cube. That doesn't sound like that much, right? Yeah, it's not that much, right? And so to get 1 cubic kilometer, what you'd be doing is taking the amount of lava that Kilauea is producing now, which would be about 2 big cinder trucks every minute coming to your yard, and for 10 years. So you'd have a little bit of cinder by the time that operation was done, right? So 2 of the biggest ones you see on those big semis with the large trailers that dump, right? 2 of those every minute dump in your yard for 10 years, and you get a cubic kilometer of stuff. So even though it doesn't sound like much, I also calculated for you people that are grown up on the Big Island that a cubic kilometer of rats, there'd be about something like 15 trillion rats in a cubic kilometer. So you might actually be able to put all the rats on the island into a cubic kilometer and stuff. And then I have a bunch of other things that you just don't even want to hear of what you can do with a cubic kilometer. But this is a lot of stuff. And for example, you can take the amount of lava that's in Mauna Loa volcano, and you can take it on the equator and not just pave the equator. You can put a block of rock that's 3,000 feet wide and 3,000 feet tall, go around the Earth 1.5 times if you unwind Mauna Loa volcano. That's one single volcano, right? Admittedly, it's the biggest one in terms of volume. So now we've answered a question that we didn't even start off with: which one is the biggest? There, that's how professor works. It's a time-honored thing of bait and switch your topics in class, and then on the test, ask a completely unrelated question. Kilauea got way demoted. No, it's demoted. Yeah, so it's actually, this is, the gain up here was from Kilauea, and the loss is Kilauea's loss down in here, because we did submarine dives on it, and we found out that it's just a thin veneer on the side of Mauna Loa underneath its summit. So most of that stuff up in there that comes up, what's above water is all Kilauea, but it doesn't go that far down underneath water, underwater. So it's kind of a wedge sitting on the side of Mauna Loa.
But it has potential.
It has potential, that's right. It's got potential. This is, we could all grow up to be president, which is a frightening thought. So we all have potential for one thing or another. So Kilauea is still building. It's active, it's young, it's healthy. You know, it's got a long ways to go. So now we can like bait and switch one more time and just go like, forget these things on Earth. Okay, so ours is 45,000 feet. If we go to Mars, this guy comes up from here and goes up here. It's 80,000 feet tall. Right? Olympus Mons is the hands down winner in our solar system of largest volcanoes. 80,000 feet tall, and I put the Hawaiian island chain on for scale. So it's about from here to Kauai across. And if you look at the caldera system in here, you can handily drop our island into its caldera and lose it. Right? So this thing is big, and what's interesting about this is roughly the volume that's been put out in the 80 million years that our hotspot's been active. Okay, if we tried to do this on Earth, if we didn't have plate tectonics, our crust is about, it's about 1/10 the thickness that Mars crust is. And so it would just go glurp back into the interior of the Earth. You couldn't put something that big on our planet. It would just start sinking back into the Earth in here just from the weight of it. So I guess I haven't really answered that question, have I, on which one's the tallest? And this is kind of the conversation I had with this poor lady on the phone with the Jeopardy thing. I don't know what her long distance bill was because I don't know if she had a cell phone or not. But I had to like think about all this. What does that mean to be the tallest volcano, right? So you can do the Wikipedia thing and just say, okay, from here to here, but is all that really Mauna Kea? From here to here, is it really 33,000 feet? Or is a good chunk of that, about 18,000 feet of that, Kohala, you know, or 15,000 feet of it? So we don't know for sure, but it kind of begs the question of who is the tallest one in here. Mauna Loa, if you measure it from where it's bent down, it's probably a little taller than Mauna Kea. And so it's, you know, the 45,000 feet. So it really depends on how we're measuring, what we're measuring from. And I know there's a couple of at least semi-physicists in the back there, right? And we all know that as soon as you measure something, you change it, right? Isn't that one of the axioms of these things? So it's hard to actually measure anything and get the true value of it. So when you go home tonight and people ask you what you learned, you can say, nothing. So anyway, so with that, I don't want to cloud your heads anymore. They filled it with a lot of nothing. And so thank you very much for coming.
So I think we have time for a few questions. So go ahead.
Only if you don't want a real answer. Yeah.
I'd like to know why Mauna Loa and Maunakea are so close to the same height.
Why they are so close to the same height? You mean why? I mean, I think the fundamental question, let me just recast it in the question I want to answer instead of the question you're asking. But why are volcanoes of different heights along the chain? And that's something we don't know, right? Mauna Kea and Mauna Loa, maybe it's just serendipity because Mauna Kea is built on the site of Kohala. But we have these things of all sorts of different sizes, right? And this is part of the fluctuation of the amount of lava coming out of the hot spot with time, right? That we're seeing it fluctuate. And then some of them growing like Hualalai, we're at a time of high productivity. Hualalai never got that big, right? Mauna Loa got a lot bigger. So that's a question we'd all like to know the answer of is what controls this flow of magma through these systems? What makes one of these guys bigger than the other one, right? And why they arrange themselves the way they do are still fundamental questions we're trying to figure out.
Why do they call it submarine?
Why what?
Do they call it submarine?
Call it a submarine age? Oh, a submarine ridge? Oh, because it's underwater. It's a ridge of rock underwater. So we call it, and that was the question too, is subaerial means it was above water and submarine means it was below water.
Are there any magnetic anomalies on the island that cause a hiker's compass to deviate?
Yeah.
Where?
Well, our rocks have a lot of magnetic minerals in them, so you could get in that problem in a lot of places. So they shouldn't cause a lot of deviation, but you can get deviations along the rock. So you don't want to put your compass right on the rock like geologists do. It just depends. Like sometimes you see it, sometimes you don't.
Well, it's finding rejuvenated eruption on
Why do we have so much rejuvenated magnetism on Haleakala? That's it's another really anomalous volcano where it actually never really, it did erode because we had the big valleys, but lava production kept going through it, much more than like Kohala, which has been shut off for 120,000 years. There seems to be an almost continuous record of volcanism on Haleakala. And it's another one of these things, exactly that same question of why are we seeing more activity on certain volcanoes than other volcanoes? But we don't really have a good answer for that. I mean, that's something that if you're younger here, those are questions that are still yet to be asked. There's a whole host of questions like that out there that we haven't figured out a way to answer them yet.
On the show How the Earth Was Made 10, 15 years ago, they talked about...
Are you going to ask me about my role that I played on that show?
Yeah.
Oh, good.
They talked about.
That was back when I was more photogenic than I
Are
was now.
the islands, moving northwest?
Uh-huh.
But as they move, they're sliding off of a mound created by the lava plumes and stuff. So that they're eroding and they're sliding off of this mound. And that's why, as you go down further, there's more underwater.
Well, we're definitely, as we come up over, you heat the crust and it becomes more buoyant and rises up.
Right.
And as it moves away, it sinks down in the long term too from that. Whether or not there's any slip at the interface between the crust and the mantle is something that we haven't been able to measure directly yet. So some people think that the crust is slipping on that interface. Other people think it's attached to that interface. So we don't really know if it's slipping there or not.
But if the weight of the island, of the volcanoes on the island, is creating a depression, and then it's got to come over, and if they're saying that it's slipping as the island moves northwest, it's slipping off the mound of the plumes. Is that true?
Is that true, John?
It's the Hawaiian swell, which
Yeah.
is holding it up.
Well, the Hawaiian swell is the heat, right?
No, it's the actual material that's rising, I think.
Right, but it's
Because off of the gravity, it tells you, if it was just heat,
well, no, I mean, it's hot mass coming up.
it's a hot mass, but it's actually moving. It's
Yeah.
holding it up. Dynamic.
But whether or not the crust is sliding off of that or not
And as
is,
it moves, it runs over this swell, is what he's talking about.
yeah.
If we weren't on the Hawaiian swell, the position of the coastline would be at about the elevation of 3,000 feet or so on this island. We're actually being held up by about 1 kilometer.
Right. Yeah,
And then
we're-
that's what he's talking about, I assume.
yeah, so,
And so when I was teaching geology, I would say, why is this island so big? It's because all the others are very small. And the reason this one's so big is because most of it is being held up.
yeah.
Yes,
and then
that was the answer on the test.
So if a large chunk of the caldera falls off and sloughs off into the sea, is there a rebound because suddenly the island is less heavy?
There probably would be, but nobody's been around to measure it. I mean, and yeah, you'd lost half your instruments, and so it's a good question. And there's evidence that suggests that we maybe have tsunamis that run 500 feet up the islands in those events too. So I don't know if we'd be around just wondering if that was the major question: is the island rebounding at the moment or not? But let me get.
I was just wanted to know how the volume compares to the flood basalts.
The big flood basalts? We are smaller than the big flood basalt provinces, right? So if you look at those guys, we're in that. I mean, if you look at our island, if you look at the whole chain, we're way bigger than any flood basalt province. If you look at just segments of it, it's smaller than a lot of the flood basalt provinces. So, I mean, they have single lava flows that are 1,000 cubic kilometers. So they're really, really big.
On one of your early slides, you showed, I think, for the anchor chain.
Uh-huh.
And it was very clear there was an angle to what was that change in angle.
Oh, John's looking at me like, what story am I going to get out of this? That's another, depends on who you listen to. There are a couple different ideas in there. One of them is that there was another plate to the north of us with a spreading ridge, so a place that ocean crust was being produced. And that plate got subducted along with its spreading ridge at about that time. And so when that disappeared, then the main motion was driven from the East Pacific rise over by South America. There's other ideas that the hot spot was drifting to the south after it moved underneath that ridge, and there really wasn't much motion on the plates at all at that time. but it was hotspot drift down to about 45 million years ago. And there's a couple other ideas too. So we don't know everything about these things. People have ideas, but we haven't so far been very good at getting motion in the mantle. Right? We don't really know what the mantle is doing so much. We do know what the crust is doing really well now, right? Because we have instruments all over the crust. So that's a big advance. But what's going on inside the planet, we don't really have a good handle on. Way in the back.
What is your speculation of the Hina cloud in the Hawaiian volcanoes, the creation of it?
The which?
The Hina flower, silver sword.
My speculation on that?
Of the creation of it.
I don't think I have a speculation on that. All I can tell you is, like, the one thing that we do know is that after that bend, then we had about 15 million years, 10 to 15 million years, where no islands were produced, that all the volcanoes were below sea level. So anything that was living on the island chain before that didn't make the jump to the modern Hawaiian Islands, starting with the Northwest Hawaiian Islands. So, and that fits out with what biologists say, that somewhere around 20, 25 million years ago, things started populating the islands here. So life has been on here for about the last 25 million years ago, which is another geology thing. Since the volcanoes got above water, that you could actually put things on and things could migrate down the chain. But in particular, animals and plants and things like that, that's outside of my realm of knowledge. Did you still have a question?
Yeah. Robin Boltham's thesis that that northern arm of the Puna Canyon is actually part of Kohala rather than Maunakea.
It's not really part of Puna. It's what we call the Hilo Ridge. The Puna Ridge is the one attached to Kilauea.
Okay. Is that definitively proven yet as part of the Kohala, and what evidence is there for that?
Well, the evidence, it's a theory, right? So in science we have hypotheses, which means it's an idea you can form a test for. And a theory is something you're testing, but the results seem to match what your ideas are, or they produce predictable results. In geology, we kind of do these multiple working hypotheses theories where we're just trying to match the information to it. So I think what we're looking at in there is the submerged shorelines are at the same elevation on both sides of Mauna Kea, and also the gravity connecting it through there are pretty strong evidence that that's probably that one single volcano. Is it for sure? No, it's not. It's not elevated to a fact or something like that, right? So, but it's a working theory that I think most people accept now. That's, and I was pretty skeptical of it when Robin first said it. So, but it's, people have worked on it and got information. So that was a good idea like his, to throw out a hypothesis and get it tested. And Robin's very good at throwing out hypotheses. He's done a lot of them and working through things too. But he's had really good vision on a lot of things and been able to toss out ideas that other people then worked on too.
Would coral be one of the things that you would use as a data point?
Well, the corals are definitely what give us the sinking, but those shorelines don't necessarily have coral on them. So the corals, and off of the Hilo side in there, we haven't had any luck getting any corals off of those deep shorelines out there. So they'd be great if we could find them, but haven't found enough.
One more question, and then we'll pick up.
Oh, right there?
Yeah, my question kind of related to hers about the bend in if the north and south poles had been in a different place 43 million years ago, and then they changed 43 million years ago to where they are now, would the rock in the seamounts, the Emperor seamounts, show a different variation of what's north to what is in the Hawaiian chain?
Well, if you're talking about the spin axis of the planet changing,
yeah,
then that seems to be related to the production of the magnetic field. And so that's an idea that originally people used from paleomagnetic data, and they called it polar wandering, where they thought the poles actually moved. But then what they did later on is they found out that you could actually go to different continents and see these polar wander curves. And then if you closed up the tectonic movement of the plates and brought them back, the curves would lay on top of each other. So we got a pretty good idea that the poles didn't actually drift. There's a little teeny bit of drift to the poles, but not very much. And really what's happened is that the rocks moved apart. And so the original idea was the poles did drift, that they had moved, the poles of the Earth were moving. But as people got more data and got more ages and stuff, they realized and figured out plate tectonics, they figured out that that was actually the cause of it. So you'll still see things called polar wander curves.
Yeah.
God only knows why geologists still call them that, but we do. They have nothing to do with polar wander whatsoever. So, all right.